Assalamualaikum, students and friends. Welcome to my tutorial in high school chemistry. Today's episode focuses on solving problems involving pH, pOH, and concentrations of hydrogen and hydroxide ions in acidic and alkaline solutions. Just hang on, watch and learn. The question is, number 1, the pH of a certain solution is 4.5. What is the concentration of the positive hydrogen ions in the solution? Number 2, what is the positive hydrogen concentration in a 5.7 times 10 to the negative 3 molar calcium hydroxide solution? In question number 3, you are going to complete the entries in the table. For each number or letter, alright, in the first column, you have to provide the pH value of the solution. In the second column, you have to calculate the hydrogen or positive hydrogen ion concentration. And in the third column, you have to give the value of the pOH. And in the fourth column, you have to also calculate for the negative hydroxide ion concentration of the solution. And finally, in the last column, you have to identify if the solution is an acidic, basic, or neutral solution. So for letter A, what is given is the positive hydrogen ion concentration equal to 5.4 times 10 to the negative 4 moles per liter. In letter B, you're given the negative hydroxide ion concentration 7.8 times 10 to the negative 10 moles per liter. In letter C, you are given the pH value 10.75, and in letter D, you are given the pOH value equal to 5.00. Just to refresh our key concepts in this topic, pH, or the power or potential of hydrogen, is a measure of acidity and basicity, also known as alkalinity, of a chemical solution. pH measures how concentrated a solution is in terms of the number of moles per liter of the positive hydrogen ions present in the solution. Acids have large positive hydrogen ion concentration, and therefore they have small pH value lower than 7. On the other hand, bases or alkaline solutions have small positive hydrogen ion concentrations, and therefore they have large pH values higher than 7. A pH equal to 7 corresponds to a positive hydrogen ion concentration of 1 raised to the negative 7 mole per liter, and pure water has a pH of 7, so it is considered a neutral substance, meaning The positive hydrogen ion concentration in water is just equal to the negative hydroxide ion concentration. Measurement of pH is in logarithmic scale. That means for each digit change in pH, the acidity or the positive hydrogen ion concentration changes by 10 times. For example, we have solution X given its pH of 2, all right, and another solution Y with its pH 3. We say that solution X has 10 times more positive ion or positive hydrogen ions compared to solution Y. And supposing you still have another solution Z, whose pH is equal to 4, we can also say that solution X has 100 times more positive hydrogen ions compared to solution Z. And to calculate for the pH value, all right, based on the positive hydrogen ion concentration, we just use this formula. pH equals the negative of the base 10 log or logarithm of the uh, positive hydrogen ion concentration. All right. So this formula is read as the negative of the base 10 log or logarithm of the molar concentration of the positive hydrogen ions. And if you're doing the reverse, right? If you're calculating for the positive hydrogen ion concentration, denoted here by bracket, capital H with superscript positive sign, all right? That will just be equal to the antilog of the negative value of the pH, all right? Now, uh, there are some calculators or scientific calculators where you can determine this antilog value of a given number, all right? So just look for this, what do you call, a key, all right, in the key pod of your scientific calculator, all right? This is what represents the antilog, also known as the inverse logarithm. So if you're going to press this number or key and then enter uh, the value, the negative value of the pH, then you will be getting the value of the positive hydrogen ion concentration. Since pH is measured in water-based solutions, there is always a balance between hydrogen ions and hydroxide ions. All right? This is because water can break down into these two ions, right? As shown in this equation. Now, at room temperature, the balance between the positive hydrogen and the negative hydroxide ion concentrations in water are related, all right, by this expression, all right? The number 1 times 10 to the negative 14, all right, is just equal to the positive hydrogen ion concentration multiplied by the negative hydroxide ion concentrations, all right? So that number actually represents the product of the two ion concentrations, all right? And that corresponds uh, to the pH 14. All right. So, based on this expression, we say that the more hydrogen ions a solution has, the fewer hydroxide ions it must have. Or, the more hydroxide ions a solution has, the fewer hydrogen ions it must have. So, to reiterate the two formulas for determining the POH, or the power of hydroxide, all right, we just use this formula, all right. This is if the negative hydroxide ion concentration is given. So we just get the negative of the log value of that negative hydroxide ion concentration. All right, you will get the POH value of the solution. Likewise, for determining the value of the pH in terms of the concentration of the hydrogen ions, positive hydrogen ions, all right, we also use this formula. pH equals the ontilog of the negative value of the uh, hydrogen, positive hydrogen ion concentration, all right. So let's now answer the given questions. All right. For question number one, the pH of a certain solution is 4.5. What is the concentration of the positive hydrogen ion in the solution? All right. So its pH value is given 4.5, and we are looking for the positive hydrogen ion concentration. All right. And using the formula for that, which is equal to the ontilog of the negative value of the pH. All right. So we determine the ontilog of negative 4.5, and we will get the positive hydrogen ion concentration, all right, of the solution equal to 3.2 times 10 to the negative 5. The unit, of course, is mole per liter, which can also be considered as 3.2 times 10 to the negative 5 molars. In question number 2, what is the positive hydrogen concentration in a 5.7 times 10 to the negative 3 molar calcium hydroxide solution? Our target variable is the positive hydrogen ion concentration, and we are given the molarity equal to 5.7 times 10 to the negative 3 moles per liter. That's the same as molars, all right? So we first calculate for the POH, all right? Since the solute is calcium hydroxide, hydroxide being a base or alkaline substance, therefore we can determine the POH value using the formula negative log of the negative hydroxide ion concentration. All right. So, negative log of 2 times 5.7 times 10 to the negative 3. Alright? Uh, this is the molarity of calcium hydroxide. Okay, we multiply it by 2 because based on the formula for calcium hydroxide, there are 2 hydroxide ions. Right? So, doing our math, we will get the pOH value equal to 1.94. So that's the pOH value of the solution. Hence, we can determine the pH value by just subtracting 1.94 from 14.0, and that will give us 12.1 as the pH value of the same solution. We can therefore proceed in getting the positive hydrogen ion concentration, all right, using the formula antilog of negative 12.1. Again, using our scientific calculator, the positive hydrogen ion concentration is just equal to 7.9 times 10 to the negative 13 moles per liter, or molars. Moving on now to question number 3. All right. So question number 3 have 4 sub-questions, A, B, C, and D. So for question 3A, we are given the hydrogen or positive hydrogen ion concentration equal to 5.4 times 10 to the negative 4. That's understood to be mole per liter. And we first determine the pH value using the formula antilog of negative 5.4 times 10 to the negative 4. Okay, we will get pH value equal to 1.0. All right. So with that pH of 1.0, we can say that the solution is very acidic. So we can continue determining the negative hydroxide ion concentration, all right, using this formula. 1 times 10 to the negative 14 divided by 5.4 times 10 to the negative 4. Earlier, we said that this value, 1 times 10 to the negative 14, is the product, all right, of the concentrations of the hydrogen and the hydroxide ions, all right? And since you already know the concentration of the positive hydrogen ions, which is 5.4 times 10 to the negative 4, so we can determine the negative hydroxide ion concentration using this formula. So again, doing your math, we will get the concentration of hydroxide equal to 1.9 raised to the negative 11. Okay, that's in mole per liter. Likewise, since we already know the pH value equal to 1.0, we can now get the pOH value by just subtracting 1.0 from 14.0. So we get 13.0 as the pOH value of this solution. All right. And continuing on to question letter B, all right, where we are given this time the negative hydroxide ion concentration equal to 7.8 times 10 to the negative 10. That's understood to be mole per liter. So from here, we can get the um, pOH value, all right? We just we just get the negative of the log or logarithm of 7.8 times 10 to the negative 10. So using your scientific calculator, we will get the value 9.1 as the pOH, all right? And of course, the pH value is simply 14.0 minus 9.1 or 4.9. So this solution is considered acidic, all right, because its pH value is lower than or less than 7.0. And continuing with determining our positive hydrogen ion concentration using the formula, the antilog of negative 4.9, all right? So with the help of your scientific calculator, we will get this concentration of the positive hydrogen ion equal to 1.3 times 10 to the negative 5 moles per liter or molar. For question number 3C, we are given the pH value equal to 10.75. Hence, the pOH is 14.0 minus 10.75 or 3.25. The positive hydrogen ion concentration, therefore, cannot be determined. All right? Just get the antilog of negative 10.75 using our scientific calculator once again. That positive hydrogen ion concentration is equal to 1.78 times 10 to the negative 11 moles per liter or molars. All right? So since the pH value is higher than 7, this solution is considered a basic or an alkaline solution. Okay? Now, for the negative hydroxide ion concentration, again, we just divide the number 10 raised to the negative 14 divided by 1.78 times 10 to the negative 11 and get the value 5.6 times 10 to the negative 4 moles per liter or molars. And lastly, for question letter D, we are given the pOH value equal to 5.0. So, the pH value would be 14.0 minus 5.0 or 9.0. So again, it is a basic solution or an alkaline solution with its pH higher than 7. The positive hydrogen ion concentration, again, is computed by getting the antilog of negative 9.0. With your scientific calculator, we will get 1.0 raised to the negative 9 moles per liter or molars. And lastly, for the negative hydroxide ion concentration, okay, again, we divide the number 1 times 10 to the negative 14 by 1.0 times 10 to the negative 9. So we will get the negative hydroxide ion concentration equal to 1.0 times 10 to the negative 5 moles per liter or molars. We now present the completely filled table as shown here. So once again, we emphasize if the positive hydrogen ion concentration is higher than the negative hydroxide ion concentration, we say that the solution is considered acidic, right? But if the negative hydroxide ion concentration is the one higher, okay, compared to the positive hydrogen ion concentration, then the solution, okay, is considered an alkaline or a basic solution. So that concludes our tutorial. Till the next episode, mabuhay, alhamdulillah, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.